Today we are going to discuss the kinetic theory of gases. See here, before going to start the kinetic theory of gases, the kinetic theory of gases, it explains the relation between macroscopic properties of the gas to the microscopic properties. So here the macroscopic properties like the pressure, the volume and temperature, whereas the microscopic property like what about that kinetic energy and momentum and velocity. So in this chapter, how this pressure and volume and temperature can be related to the kinetic energy or volume or velocity and this momentum. See here, before going to discuss about this kinetic theory of gases, they define some assumptions. So what are the assumptions of the kinetic theory of gases? First here, the molecules which have lesser in size, first molecules. Next, the separation between the molecules. Suppose this is the molecule, this is the molecule. This separation, suppose let this D here, compared to that size, this size compared to the separation between these two molecules, this size is very, very less. Next, third one, these molecules, it obeys the Newton's laws of motion. In the mechanics, we are going to discuss the Newton's laws of motion. Next, let this molecule, it moves. This is, we are defining some x-axis and y-axis and z-axis. The velocity along this Vx, along the y-axis Vy, along the z-axis Vz. Here, the majorly assumption that the probability is traveling along the x-axis will be equal to Vy will be equal to Vz. Next, suppose this is the vessel, let this is the molecule, this is another molecule, let there is a collision between this one and also a collision between this wall. That means the collision takes place between these two molecules or between the molecule and wall. Then only force exerts. Otherwise, we can neglect the force. This is the another assumption, except collision, there is no force. There is no force exerted. And one more thing, let these molecules, there are so many number of the molecules, the gravitational potential energy between those two molecules, the effect with them is completely negligible. That means there is no gravitational potential energy between the molecules, is completely negligible. And the final most important assumption here, the kinetic energy of these molecules is directly proportional to the temperature. So these are the assumptions before going to start this kinetic theory of gases. First, the molecule size is very, very less. Comparing the separation between the molecules, their size is very, very less. It follows the Newton's laws of motion, and the probability of the traveling along the x-axis, y-axis and z-axis will be the same. And next, except collision among the molecules or the molecule between the wall, there is no force exerted. Only during the collision only there is a force exerted, and gravitational potential energy acting on these molecules is completely negligible, and kinetic energy is directly proportional to the temperature. So based on these assumptions, we are going to find out the pressure exerted by the molecules. This is the vessel. See here, generally we are taking some three-dimensional one. Let our assumption here, the molecule, it moves along the x-axis. Let this is the x-axis, this is the y-axis and z-axis. Now I wanted to find out that pressure exerted by the molecule on the wall. See here, this is the mass of the molecule. It travels along the positive x direction with velocity some Vx. See here, after the collision, definitely the collision between the molecules or walls constitute to be the elastic. This is one more assumption. Then this molecule, it comes this side, the mass is same, but we are taking the positive x-axis Vx, so negative x-axis Vx minus Vx. Therefore, the change in momentum of the molecule is equal final momentum minus initial momentum. So, this can be minus mvx minus of mvx. So, this can be 2 minus 2 mvx. See, this is the change in momentum of the molecule according to the conservation of momentum. So, change in momentum of molecule plus momentum of this particular wall will be is equal to 0. So, delta P of the wall is equal minus delta P of this molecule. So, delta P of the wall is equal minus of this one. So, we can write down 2 mvx. According to the Newton's second law, the force is equal delta P by change in momentum with respect to time here. Let the length of this vessel is L. For moving towards this direction, what is the time taken? Delta P by this time here L by Vx. Again returning same time L by Vx. So, this delta P what we are getting 2 mvx by 2L by Vx. 2 gets cancelled, m v square x by L. This is the force exerted on the wall by the molecule is equal what we are getting mv square x by L. See here, let n number of the molecules are present. We cannot show that only one molecule, there are so many molecules. Here our assumption is n number of the molecules are present. Therefore, force exerted by all the molecules by n number of molecules, this can be n mv square x by L. I am taking this will be what should be that v1 square plus v2 square and so on Vn square by n. Here we can write down n m by L. This is the average square because V1 square plus V2 square and so on Vn square, average square by n here. So, here we can write down average velocity here V1 square plus V2 square and so on Vn square by n under root of this. From this we can write down this one F is equal, if we are substituting that n m by L into V prime here this square. See, this is along the x component, our assumption is along the x component. But according to the kinetic theory assumptions, Vx, Vy is equal to Vz. So, we can write down V is equal to under root of V square x plus V square y, V square z. This is the magnitude. See here, if Vx, Vy, Vz is equal to V here, then we can write down directly 3 V square x. So, V square is equal 3 V square x, V square x is equal V square by 3. See here, f n is equal n m by L here, V square by 3. From this, what we understand from this, 1 by 3 n m by L into V square. See, our aim of this particular expression is to find out the force of pressure. This can be force per area. So, this can be what is that n m by, so L A into V square. So, this we can write down n m, L is equal to volume here, this is V square, this is the mass of one molecule, this let this n is the number of the molecules, we can write down this can be total mass of these molecules gas by V into V square. So, we can write down P is equal to 1 by 3 rho V square. So, this V we can write down as a VRMS. So, V square RMS is equal 3P by rho V RMS under root of 3p by rho. So V RMS is nothing but it's a root mean square speed. This can be what is it under root of 3p by rho. So our conclusion from this derivation is P is equal to 1 by 3 m by v into v square RMS. We can write down another thing here. PV is equal to 1 by 3 m v square RMS. See, again from that we can explain this kinetic energy. This can be equal to what is it 1 by 2 of mv square RMS. If you are substituting from this PV 1 by 3 we can write down as 2 by 3 into 1 by 2 mv square RMS. So I am taking 1 by 3 mv square RMS is equal 2 by 3 into 1 by 2 mv square RMS. See here 2 by 3 we can write down this is a translational kinetic energy. So therefore the translational kinetic energy here this can be equal to 3 by 2 PV. This is the another conclusion from this derivation. This is the first derivation. What is it? V RMS is equal under root of 3p by rho here. This is the pressure exerted. This is about the density of the gas. Next conclusions from this main expression. We know that VRMS is what happens directly proportional to the temperature here. We can write down PV is equal to 1 by 3 m V square RMS. From this equation, how can we derive that gases laws like Boyle's law, Charles laws at constant pressure, Charles law is constant volume, and Avogadro's we are going to discuss now. See, suppose we are taking first Boyle's law here. What are the conditions here? Constant temperature and given mass of the gas is constant. So here if it is maintained as a constant temperature, definitely what happens that PRMS is directly proportional to T here. As the temperature is maintained constant, your VRMS has to be maintained constant. So we can write down PV is equal 1 by 3 mR square. This directly proportional to some constant into T here, because 1 by 3 m is a constant. See here, as constant temperature, m is also constant. We can write down this total KMT will be equal to another some constant K prime. So here what we are getting finally, PV is equal constant. So now we are deriving the Boyle's law from this expression. Come to the Charles law at constant pressure. See here the P is a constant, and first P is a constant and mass of the gas is a constant. See here m is a constant and P is a constant. We can write down PV is equal to 1 by 3 mv square RMS. So here the constant pressure P is a constant and VRMS is constant. We can write down directly this can be proportional to T here. So PV is directly proportional to K here. Again this P is a constant, so we can directly write down V proportional to T. This is about the Charles law at constant temperature, at constant pressure. Now Charles law at constant volume we are going to discuss.